Okay, hi. My name is Sean Floyd. I'm here from Berlin, Germany, and from Zalando. I'll be speaking today about hacking Java. Yeah, so first, to give you some background, I've been around the Java world for long enough that I have chosen the handle Old Java Guy. So I've worked with Java for most of the last 20 years or so. These days, I'm mostly doing Scala, but still, I'll actually be talking about some non-standard Java stuff in this talk. Okay. This talk is about things you don't usually learn in Java. So about when you look at Java, it's a huge infrastructure, and there's many things happening there that you don't see in everyday life. So this is not about best practices. This is about esoteric techniques. Some of them can be used in production. Some of them perhaps not. We'll actually go into that. And there is a companion GitHub project. The link is there, the Bitly Hacking Java. I would encourage you to look into that because for every single technique I'll be talking about today, there's a little sub-project with unit tests and sample code, etc. So this talk, as I said, is about non-standard Java techniques, and I would like to, I need to sort of have an agenda, a red line that draws through the talk. So I chose to come up with several use cases. And these are the three use cases I'll be covering. The first one is value objects, or data transfer objects, as the older people sometimes know it. Just standard objects that just carry state between layers. The second part will be patching a third-party library. I hope all your alarm bells went on, which is good, but still. And the third part will be compile time code effect analysis. So tools that actually, that make the compiler smarter or replace the compiler with something differently, etc. So. And so the common pattern is that all of this will be code that interacts with code, that analyzes code, or that enhances code. Let me turn this off better. Okay. So this is the GitHub project, set up as a multi-module Maven project. Maven is not the latest, coolest, but as I said, I'm an old Java guy, so I'm also the old Maven guy. And I think it's good enough. And the first use case I'll actually be going into is value objects. So a value object is just an object that usually has a few properties. But in Java, if you've all read this book, Effective Java, which I hope you have, otherwise please go ahead and read it. You're not a good Java developer until you've read and understood this book. According to this book, you want your value objects to have several methods implemented: equals, hashcode, toString, getters and setters if it's mutable, or getters and constructors if it's immutable. Perhaps you want factory methods, perhaps you want builders, perhaps you have additional requirements like serialization in whatever is your serialization technology, etc. All of this is very verbose, very painful in Java, and it looks like this. So here you can see there's actually this whole class just has these two little properties, property 1 and property 2, and the rest is boilerplate. It's just the standard boilerplate. It's getters, it's a constructor, equals and hashcode, and toString. So this is just the basics. And for comparison, why I find this painful, I'll show you the same thing in Scala. This is exactly the same functionality. No, it's actually more functionality because it also gives you a copy method, and it also enables pattern matching and some more things. So in Scala, that's all there is. So So let's have a look at how we can actually reduce this boilerplate, because the boilerplate, I mean, I all know the IDEs will help you generate all this boilerplate, and perhaps if you're lucky, you'll find the IDE that does it exactly the way you like it to be implemented, because there's, of course, as always, there's religious wars there. So in the equals, basically, in an equals method, you can go two ways. You can go with instance of or with get class, and there's a religious war, and both sides have strong arguments, and so on. And there you won't find any IDE that will implement compare to in a sane way, etc. So this is all very verbose and painful. So let's look at tools that help reduce the pain of this. And as I said, I will have I have all of this covered in unit tests, and so for this part of the functionality, I created an abstract test suite that will expect a certain structure of value object, which is like this. So I have a user with a first name, last name, birth date, and a list of addresses, and address is another value object. And since this is the test project is a separate project, so it doesn't know the implementation type, so it will have to loosely couple against this, and that will be implemented basically like this. So it just so it makes some assumptions on the contract of the equals and hash code method. So when two objects are equal, that implies that they have the same hash code. When you create two two objects with the same state, then they should have the same toString, etc. So there's some conventions that I can check on a very abstract level, but that's not that useful. We actually want to get at the data, and for that we're embracing an ancient convention called Java beans, where probably you all use Java beans at some time. I mean, you know that objects in Java usually should have getters and setters. That's the Java beans convention, and this is how you can actually read those Java beans through the introspector mechanism. This is not production-ready code. This is test code. So in production-ready code, I'd probably do this a little more carefully here. You just see if there's any exception pops up, I'll just rethrow it. That's not how you do it in production, but for tests, it's just fine. So what this method does is it gives me, it creates a map from string to object from all properties a field, a class has. So if you have a class that has properties foo and bar, then there would be methods get foo and get bar, and the introspector would find these as properties named foo and bar, and would provide access to the read methods, and the read methods I call here reflectively. As I said, it's hacky, but the talk's called Hacking Java. So this is what I'll be using to test the individual solutions I'll cover next. The alternative to that would have been a test suite that the Guava guys from Google have created, which is actually pretty cool. It's called Abstract Package Sanity Tests. So when you, if you come in a situation where you're actually building a library where you want all your top-level classes to fulfill standard Java contracts, this is a very nice builder for creating the basic sanity tests. So not the real tests on application level, but just the that nullness works well and that equals works well, etc. So I considered using that, but my needs were more specific. So I'm getting closer to the first actual technique. What I'll give you first is annotation processing. It's basically the only API the Java compiler gives you. So the Java C compiler I think the first version was introduced in Java 1.5, but in 1.6 it was remodeled as JSR 269. Pluggable annotation processing, which is basically, so you implement an interface called annotation processor, or I think it's just called processor, and you have somewhere on your class path, you have this magic file, metainf/services/javax annotation blah 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 processor, and that contains the list of fully qualified processor names, and if the compiler finds those anywhere on the class path, it will instantiate them before the actual compilation. So it's a separate compilation run, actually multiple runs that run on annotations before your actual class data is processed, which leads to some subtleties about annotations. For example, annotations can only contain compile time safe data, so you can never actually execute any code in an annotation because the annotation compilation is in a separate cycle, so it needs to be constants only. So you can use that's documented. But I will now introduce some techniques that are implemented using annotation processing. The first one is relatively well known, Project Lombok. It's a technique that has been introduced, I don't know, 5-6 years ago. The naming is by design. So Lombok is an island that's close to the island Java. So it's kind of, yes, it's a bit like Java, but not the same. And the Project Lombok guys did some really evil hacking. I mean, it's a very cool framework, but also a very hacky framework, because they actually misused the annotation processing API. The annotation processing API gives you read-only access to the abstract syntax tree the compiler has access to. But what they did was they cast the interfaces to the internal implementation types, and suddenly they have read and write access, and they're just rewriting the abstract syntax tree on the fly. Usually, when you do annotation processing, the standard use case is you generate separate source files. Like classic applications would be like Hibernate, etc., would look at your annotated classes and would generate a static meta model in separate classes from your annotated classes. That's a classic intended use case of annotation processing. What these guys do is they enrich your source code, your virtual source code. So actually they create source code that you don't see. It's source code that exists only between your source file and what the compiler sees. So the nice side effect of this is your classes look very lean. They look like this, for example. You just have this annotation data, which tells Lombok, just do your thing. So if you have this set up, then Lombok will create getter status equals hashcode to string. And if you say, but I want this to be immutable, then all you have to do is make your properties final. And so now Lombok will create a all properties constructor and only getters, no setters, etc. And this is pretty cool, but it's also pretty hacky. So what's hacky about it is, first of all, it's using internal proprietary APIs. So this has to be implemented separately for all the different compilers that have to be used. So the Lombok guys have implemented it for Java-C and for the Eclipse compiler, because the Eclipse compiler works differently. So in the Lombok project, you already have internals from 2 different compilers. And if any of those compilers ever changes their API, then Lombok breaks. Then you have to wait for your next Lombok version until you can use the next compiler version. So that's a bit on the hacky side. And the other hacky thing about it is, as I said, it creates artificial source code that's not there. So at runtime, your code works against lines of code that don't exist in your class. So you will, in your stack traces, for example, you will see lines that don't exist. Your debugger will go wild and won't be able to actually jump into the method because the method doesn't exist in the source code. It's usually you shouldn't have too many hard problems in your value objects, so they should be logic free. But still, it feels kind of strange that there's things I see in the source code that or that I don't see in the source code, but that actually happen at runtime. And so, well, this is the hacky approach. Then the guys at Google thought about how can we do this in a non-hacky way, and they came up with a project that's called AutoValue, which gives you a lot of the functionality, of Lombok, but it gives it to you in a well-behaved way. So it does not enhance the abstract syntax tree. It works with actual code generation. So now you're wondering, how could that ever happen? And the way they do that is through abstract classes. You define an abstract class for your value object, and you just define your getters. If you want to use JavaBeans naming convention, that's fine. If you don't want to use it, it's also fine. So they said it doesn't make sense to buy into a naming convention that was invented 15 years ago for enterprise programming when nobody is doing enterprise programming anymore. So you can go with standard JavaBeans naming conventions, or you can just call your method property 1, property 2, etc. And you have to create a static factory method. Because that is anyway the encouraged method for creating immutable objects. Oh yes, and everything is immutable. So Google auto-value assumes that all your value objects are immutable. So you mark your class, your abstract class, as auto-value. Google auto-value will generate a class that's called auto-value underscore your class name, and it will generate a constructor that instantiates the properties in this order. And the constructor does null checks, for example. So anything you have will aggressively reject nulls unless you mark your method as nullable, for example. So there's some nice convention over configuration there. It's not as powerful as Lombok, but it gets pretty close. It also both of them also support builders through special annotations, but it's actually well behaved, and it doesn't buy into any undocumented internal APIs. So this was a bit good cop, bad cop versus actually the other way around, bad cop, good cop. And now comes the crazy cop. So the crazy cop in this case is the cglib bean generator. cglib, I don't know if you've heard of that. It's a code generation library. It's actually, I talked about code generation, but what these guys mean is a different kind of code generation. They're talking about byte code generation. So here what we're talking about is dynamically creating classes at runtime. And I hope you're all wondering, why would I ever do this? Keep it up. So cglib is a framework that is used by frameworks like Spring that need to do more instrumentation than reflection lets you do, and in a more effective way. So generating methods on the fly, etc. And in cglib, there exists a playground feature which is called a bean generator, which is just an API that you pass in basically a map from string to type, and it will generate properties on the fly. So it will generate field getter and setter on the fly. And so it's really not production ready. So it only generates field getter and setter, no equals and hash code, etc. And I actually tried looking at the API and wanted to implement it itself, but once you're interacting with bytecode, it's stack programming, and stack programming is not a model that's for everyone. I eventually gave up. So what I did is, since this talk is called Hacking Java, I went the hacky way. I created the anonymous the dynamic class, and I wrapped it with a proxy that does the heavy lifting, the equals hash code and toString, etc. So this is obviously, if you look at the code, you can go, oh, good Lord, this is crazy what this guy's doing, and it is. And please don't use it in production, but it's kind of interesting to see what you can do. So I'll show you a bit of it. So this is just creating a class on the fly. So you instantiate a new bean generator. You give it a naming policy. In this case, the naming policy is very simple. It's just so we pass in a class name, and we just want to use that class name, and And this bean generator has a static method add properties where you pass in the properties. Also, it's a map, and it will generate fields, getters, and setters on the fly. And here I'm creating the class on the fly. And since I also want to make my test suite happy, creating the class on the fly is not enough. I also want to populate the class with values, and I do that with this method. Where I'm basically just instantiating the class I created earlier, and I have assigned properties. So that's a method that uses basically the opposite of what I showed you earlier. So the introspector mechanism, only this time I'm calling the write method, not the read method. And yeah, if anything happens, I just ignore the exceptions and let it crash. And then I create a proxy. So I create an enhancer. That's the CGLib abstraction that you need to use when you're creating a dynamic proxy and you're setting a superclass. So in this case, I'm creating a dynamic subclass of my value object, and I'll be delegating some of the functionality to the superclass, and I'll be handling some other in my subclass. So I'm setting this callback here, and in this callback, I have an enum of method signatures that I'm looking for, and if I find the specific method signature, then I'll handle it through a strategy object, and otherwise I'll just invoke the super method. And here's one of the examples. So here, this is the equals method, and here yeah, and here again I have DTO factory read properties. So again, I'm using Java Beans to read all the properties. So this is of course very, very, very much time complexity, etc. So not at all efficient. So I'm reading all the properties first and then comparing two maps. So that's definitely not the way to do it, which is why I marked this as don't try this at home. So the next now to get back to a bit more sanity. As I said, the CGLib guys are talking about bytecode generation, but I'll now be talking about source code generation. So source code is generation at build time. So I'll be generating source code dynamically to suit my needs. Which basically puts me into this scenario where when people ask me what do I do for work, I'll go into a dialogue that's pretty similar to this. So please don't try to explain to non-technical people that you're writing code that writes code. And of course, once you teach computers to, once you teach code to write code, etc., then you're immediately introducing Skynet. So that said, let's go into actual reasons of doing it. So as I said this earlier, there's sometimes you just want to get it exactly right and not only almost right. Perhaps you have individual ideas of how things should work, or you have custom requirements, like you want to integrate, I don't know, Jackson annotations or JPA annotations. And yeah, the good thing, you can do almost anything. The bad news is you have to do almost everything. So most people stick with either Lombok or AutoValue, but I personally use code generation pretty often, and I'll be giving you an overview of that. So here's how you can do it in the Maven build. There's actually several ways you can integrate code generation in the Maven build. I usually go for Groovy because it's the least painful way to integrate a separate process into a Maven build. So I use the Groovy Maven plugin and execute custom Groovy code. That because the advantage that gives me is my Groovy code can live in the same project as my Java code. If I want to do it with Java, then I have to write a plugin, and that plugin has to live in a separate project tree. Or I have to write a main class, and I need to set up separate compile cycles. I first compile my code generator, and then with the code generator I generate my code, and then I compile the rest of my classes. That's really messy. So with Groovy, the whole setup is the least messy. And for code generation, I'm using a framework that's called JCode Model. This is a framework that was originally created by Sun, I don't know, probably 10 years ago, and they used it for JAX-B, so basically code generation from web service specifications, and it did a job well. But then they abandoned it, and recently there was a GitHub fork, and it's now active, and that's nice. So it implements the full specification of Java 8, and it has a nice, understandable API, and it manages types for you, which is very nice. So here's how I integrate that in the Maven build. So I call the Groovy Maven plugin, and I just have a small wrapper script. The wrapper script will just call the do the heavy lifting, the actual code generation. And here's how I can model my value object setup. So if I was using this in a production project, I would have such a user DTO declaration for every value object I have. So it's just basically a map, sometimes a map with several dimensions. Here you have, if you have generics, I went for a low-tech way to implement generics. I mean, if you really want to implement generics in a type-safe way, it's really nasty and verbose. But fortunately, I'm not really interested in that. I just need, okay, it's a list, and it has and its type is address, and that's good enough for me. And so this is how my DTO generator looks. So I interact with, so code model is the main abstraction from JCode model. I tell it I want it to create this package. Has to be with underscore because package is a reserved name. Same for class. And so I have all these methods to define constructor getters equals hashcode, etc. And yeah, so this is my routine for resolving types, where I just figure out, is it this generic type? Otherwise, I'll just go for a plain type. So it's not perfect, but it gives me pretty good results. And here's one actual class where one actual method where I define a constructor and fields. So yeah, I'm creating a constructor with public modifiers, and the constructor has a body, and so I'm using a map of fields. This is Groovy code, so the map doesn't have generic parameters, but I know that it's from string to object. So I'm creating a field for every map key, and the type is what I resolved from the map value. And now I am and I'm also creating a constructor parameter of the same type and name. And now I'm assigning in the body, I'm assigning the field from the constructor parameter. So that's as code generation goes, this is pretty simple and easy to understand. You'll see worse later. And here's the toString method, where I'm actually using Guava's toString helper. So things get a bit more complicated because I actually have chained invocations. Here you can see that or perhaps you can't see, I'm using more objects.toString helper.add the next property and the next property, etc., which means I have to always store the previous invocation, because I take the previous invocation as input to the next invocation. So that's a bit tacky, but it gives you a nice fluent API. So that's basically, that wraps up the value objects part. Other things that I haven't looked into, but that are also out there, is template-based code generation. I personally don't like that. I think it's not elegant. But I see a lot of people doing code generation with velocity or mustache templates. It's there. It works. When it comes to bytecode generation, cglib is pretty old school and not that nice. So there's a new library which is very nice, ByteBuddy, but you still have the same problems. It's bytecode programming, which is not a programming model that I like, so I haven't really looked into it. But if you want to do serious bytecode generation, have a look at ByteBuddy. Then another approach that I know some people use is interface-based proxies. So basically pretty much the same thing that Google AutoValue did with abstract classes, but you would do it with interfaces. You define an interface with your getters only, and then you magically back that up with a map or somehow. That's also okay, but I had to draw the line somewhere. And then, of course, there will be a new standard for value objects in Java 9, where value objects will be promoted to a more native types. I haven't really looked into that because I don't think it solves all the problems, but it's there and you should have a look at it. That wraps up the first use case. The second use case is patching a third-party library. Now, this is a crazy scenario, and I hope you've never encountered this scenario. Unfortunately, I have more than once. So you have a boss or whatever company regulations force you to use a library, and this library is crap. You can't get rid of this library, but you have requirements that this library doesn't fulfill. Perhaps the library has bugs, or perhaps it has missing features. I've had one scenario where I've had a client who basically wanted a feature in Maven implemented that has been an open Jira ticket for about 10 years. So they said, okay, but we want that implemented, and we still want to stay current. We want it implemented in every new Maven version. So what I did was built a pipeline for them that patches this functionality into it and created a custom Maven release for them automatically in a CD pipeline. It's not what I would do for myself, but if the customer asks for it, then you have to oblige. And so here I'll be looking into two different ways of achieving this kind of functionality. Basically, you can either work on the source code or on the bytecode. So if you have access to the source code, then you should do it on the source code. But often you don't with legacy libraries, then you'll have to do it on the bytecode, and there's different ways of achieving that. And of course, you could just say, oh well, I'm an old Unix geek. I just write a Unix diff patch and I'll just apply the patch. But that's the most flaky scenario, because if they just introduce any white space anywhere, your patch will break. So that's not something I'll explore here, but just to tell you that option is of course also out there. First of all, again, I want to test everything, so I had to create a testing baseline. And so I wrote a very stupid class, which has two stupid methods. The one just converts an int into an integer, but it doesn't use integer value of, so it doesn't reuse the integers. It always creates a new integer, and also both of these set a system property. That's important, because otherwise I can't assure that the patch is actually being applied. So the system property is for me the marker. I'll be asserting that these system properties are not set in my test suite. The second class does string concatenation in a loop in a way that the compiler can't optimize away. So if you do string concatenation with plus in a loop, that's okay. But if you do it with plus equals, the compiler can't really abstract that away. So if you have a very long list of strings, you'll be doing something completely crazy. None of this are serious bugs, but I just wanted to have some low-hanging fruit, so methods that can be fixed very easily. So here's my test suite. I have two methods, actually. Only one made it on the slide. So here I check that the method is still. No, here I check that it actually uses the integer pool. So the integer pool by default caches the values from -127 to +127. So when I call this method with 123, then I will assert that the result instance is actually the same instance when I call it twice. Whereas if I call it with a higher number, then it won't be the same instance because, as I said, the string, the integer pool only goes to 127. And at the end, I'll do in the after, I'll check for the evil system property, because if the evil system property is there, that tells me my patch hasn't been applied. So now let's look at actually applying the patches. The first technique I'll be using is AspectJ. Actually a very old technique. I've read about it, I don't know, 12, 13 years ago for the first time. It's an aspect-oriented language. So it's a language which so it's basically a secondary language. You write your program first, and then you identify cross-cutting concerns that you weave into your program from the outside. It has its own proprietary format .aj, but some years ago they reinvented themselves using Java notation, where everything is based on annotation. So it comes in two flavors, and I'll be using the traditional flavor here because actually with the Java flavor there's a lot of confusion, because the Java AspectJ syntax is also used by Spring AOP. Spring AOP uses the AspectJ annotations to do a different thing. So what AspectJ does at compile time, Spring does a subset of that at runtime. And so if you're interested at all in that, read this book. This is the only reasonably good documentation about both AspectJ and Spring AOP, and it clarifies some of the misunderstanding there. But I went with the traditional syntax to reduce the chance of misunderstanding. So here is my patching aspect. With AspectJ, you usually have two parts. You have a point cut. So a point cut is basically a selector. If you guys are familiar with web programming, then it would be similar to let's say a jQuery selector. And an advice is the second part. The advice is logic that you apply to that selector. So you can have many different point cuts, and that won't actually do anything until you create an advice. And in this case, I'm using an around advice, which basically which is usually wrapped around a method invocation, but here I'm misusing it slightly to replace the method invocation. So in an around advice, you would usually somewhere in this around advice there would be the keyword proceed, which would tell AspectJ to execute the original method invocation. So you would usually wrap it with, I don't know, security checks or logging or whatever cross-cutting concern you have. In this case, I'm actually getting rid of the method body and replacing it with my Saner version. So here I'm, so with the integer method, it's very simple. I'm just doing return integer value of I. And with the other one, I'm using a string builder instead of the string concatenation. So I'm solving, so as you can see, you actually have Java code embedded into the AspectJ code. And yeah, with AspectJ can do a lot more than that. In this case, I've been replacing code, but usually you're enriching code. You can also do intertype declarations in an AspectJ. So not, and now you're going to tell me Java 8 has default methods. I know, but traits are a lot more than that. So you can have you can assign a class different interfaces that also have fields and behavior. So you can have real multiple inheritance if you go that way. Not necessarily the way you want to go in Java, but so AspectJ is usually popular in some small, more academic circles, but it is very very powerful. One other thing you can do is policy enforcement, but we'll get into that later. So the next part is, so as I said, that's on the byte code, but now let's assume that I have access to the source code. So we'll be working on the source code, and this time we can't work with J-code model, because J-code model actually is only good in creating sources from scratch, but it can't parse Java code. So this is where a different library comes in, which is called Java Parser. This is again a recently restored project that was previously dead, but it's now actively maintained. Yeah, the API is not as friendly as code model. The main pain is it won't manage types for you. So if you call a method with some objects that you haven't referenced yet, it won't automatically create the import for you. You'll have to create that import manually, and keeping tracks of imports is a real pain. The guys from this project have actually told me they're working on a meta project that will make this process more simple, but that's still very new in the making. Okay, so here again I have a Groovy maker, Groovy wrapper, and in this case Java Parser is mostly visitor based. So here I apply a patch with a new patch visitor, and so there's basically a void visitor, which by default does nothing, and has implementations for lots of different kind of declaration types. And in this case, I'm overriding the method declaration part, and I'm matching for my two buggy method names. And if there's a match, I'm just reassigning the method body with a new block statement, which is basically overriding the existing one, and then I'm calling my custom method. And so for the integer, it's pretty long. All this for basically a one-liner, but it gets worse. So basically, so for my string method, it leads to this, which of course leads to this. So it's not something you want to do with a big code base. I would try to use, if you want to do that, and you probably want to have a hybrid scenario where you have some prepared classes, some real source code, and where you just basically generate the bridge code that delegates to your real source code, because otherwise it's unmaintainable. Yeah, so the trade-off. Aspect syntax tree manipulation is very hard, very verbose, and very error-prone. You could always do it with regex in some cases, but then if you're active Stack Overflow users, then you will know what happens to you if you ever try to write an XML parser with regex, because Cthulhu, the evil god, will come and hunt you, and the same applies to a structured language like Java also. And that basically wraps up the second use case. And the third one is, oh, good Lord, I'm over time already, right? Okay, go ahead. The third one is compile time defect analysis. So basically bug hunting. I will not offer replacements for the existing legacy tools. They're checkstyle PMD find bugs working on either source code or on bytecode level. They're very good. Keep using them, but sometimes, but the problem with them is they don't really wrap into the compile process. So I'll be looking into tools to actually check your code while compiling. Again, I'll have I have written a test harness. In this case, it's a bit more complicated because I actually need to run a compilation while testing. So I'll have to abstract that away. And to do that, I created a class that I called forked run, because basically I need to create a forked Java process for each of the compilation runs and evaluate the output. And depending on the framework, I sometimes have to put libraries on the class path, sometimes on the boot class path, etc. And this forked run class encapsulates all that magic. You can have a look at that on GitHub. So here's some sample code on it. Okay, Unfortunately, detecting defects at compile time only gets you so far. So for example, I have not found any reliable way of detecting immutability. So in this case, this class is immutable, at least for practical purposes. There is no way you can mutate its internal state, but it contains some mutable members. It contains a date, for example. A date is mutable. A list can be mutable or cannot be mutable. In this case, I'm using Guava's list implementation, which is immutable, but there is no framework that can identify that without having intimate knowledge of the specific framework. So it's pretty frustrating that some things just can't decide it. But let's look at what can be decided. So we can, of course, easily forbid the usage of individual classes or class usage patterns. We can forbid certain certain packages to access certain other packages, but these days all the buzz is about microservices, so the better solution is, of course, to just tear apart the monolith and move those packages to separate services, and then you've solved that problem. But in case you can't do that, go with architecture aspects. And then, of course, there's standard bugs like nullness, for example. I mean, null is the single most evil bug pattern you'll find in Java, and has cost billions of insert currency here. So you always want something that a framework to be aware of how you use null. So the first technique I'll be looking at here is, again, from Google. It's called error-prone. It's one of the Google 20% projects, and it's now being used by Google in their own internal compilation process. It's actually a replacement for Java-C. It's a wrapper around it with a compatible API, and it has a set of known bug patterns. But unfortunately, most of them are very specific to Google. So if you code against Google's APIs, this may make sense for you, but if you don't, it only gets you that far. If you don't, then it gives you some esoteric bug patterns, like, for example, this. It will detect bad regex patterns at compile time. Nice to have, but not really essential. Next part is the checker framework, a framework that embraces annotations. So it's based on annotation processors, but I'm not sure if you know that, but in Java 8, annotations have gotten a lot more flexible, so you can put annotations on many more different cases. So, for example, on method invocations, you can also use annotations, and the checker framework is actually really embraces this functionality. And so here's, for example, a nullness check where they define some nice semantics for null. So if you look at this, it says polynull, for example. Polynull defines that this method will return null exactly only if null comes in. And you have the parameter type also annotated as polynull. So the compiler will actually check that there is no code path where this method returns null unless the input is null. And the second part here is monotonic non-null. So this is a method that so here's a variable that initially is null, but once it has been assigned to non-null, there is no code path that could ever assign it back to null. And while I'm not sure those are my favorite semantics, it's nice that the compiler can figure them out. So this is sure.
Isn't it simpler to use optional?
Yeah, the question was, isn't it simpler to use optional? Yes, of course it is simpler to use optional. I know. The thing is, the problem is developers don't always agree on one coding style. I've met a lot of Java developers who hate optional. I don't understand it. I completely embrace optional, but not everybody does. And so this is for the team that does not understand or embrace optional. Anyway, this is pretty good for this use case. And of course, for the next use case, I'll be looking at aspect J again, because aspect J also gives you policy enforcement, and that's a bit for the control freaks. So what you can do with policy enforcement in aspect J is, well, there's a lot you can't do because you cannot inspect any control flow. So basically, the stuff we figured out about nullness would be completely impossible in aspect J, because you can only inspect one specific point in time. You can say, okay, here's one method invocation, and I can look at the type of that method and the type of its parameters, but I can't have any history. So I can't say, okay, before I call this method, something else has to have happened. So because it's completely static, but it helps me when I want to keep a blacklist, for example. So let's say I have deprecated types. So a standard example would be these soft deprecated collections. So hash table is the old version of hash map, and vector is the old version of array list. And usually code that uses them are pretty bad. And if you want to enforce that, then you can just declare a compiler error here. So what you would do here is just use the aspect J compiler either in addition to the Java compiler or instead of the Java compiler, and it would throw a compile time error if either of these classes is used. And that's also often used with those with the architectural aspects I mentioned earlier. So when you have different packages in a monolith, you can ensure that, for example, the persistence layer is only accessed from the service layer, and the web layer may only talk to the service layer. That's the kind of thing you can support there. I have some examples for that in the GitHub project also. So this wraps it up, and here's a little matrix of the things I've talked about. So green means I've used this in actual production, but that doesn't mean I will actually recommend it to you. So specifically, yeah, aspect J is kind of like yesterday's news, but it's still sometimes interesting. Lombok is, yeah. So my personal opinion is Lombok is not that nice, but on the other hand, it gets a lot of visibility. So for example, the Spring Data guys are using it, and you don't have any runtime dependencies. You just have the compile time dependencies. So once you build this green, everything is fine. Yeah. That's pretty much it. So if you want to, look at the GitHub code. If you have any questions, ask me either now or later. And so, which leads me to the question slide. Any questions? Yeah, go ahead.
Did you mention the issue with Eclipse compiler when using annotation processor?
No, I actually haven't been using Eclipse for the last 5 years or so. So, but
The problem is lots of people are using Eclipse, and it will break your annotation process.
Why?
Because the compilation process is not the same. It's incremental compilation.
Okay. No, I mean, I've touched Eclipse internals when looking at Lombok, but I would say if you have well-behaved annotation processes, that should not be an issue. But it's probably the hacky ones that cause the issue. Okay. Anyway, yeah. So finally, I was sent here from Zalando. So if you, we are hiring about 1,000 new developers in Berlin, Helsinki, or Dublin. So if you're interested in that, approach me afterwards, or look at our tech blog, look at our GitHub repo and our Twitter. And apart from that, thanks for listening.